tunnel junction, and next to this magnetic tunnel junction you have a wire. And just similar to these first experiments from Ørsted, when you pass a current through this wire, it generates a magnetic field that changes the magnetic state of these magnetoresistive elements. The problem is, if you want to follow Moore's law, where you make things smaller and smaller and smaller, it's very hard to do when you need to apply a small magnetic field at a very small area. And so for the last 10 years, there was lots of interest of working with so-called spin polarized charge currents. Now there, what happens is, if you take a charge current and you spin polarize them, and I'll talk more about that a little later, then the spin polarized charge current, when you have it enter into a magnetic material, it may also change the magnetization of this magnetic material. And this is known as spin transfer torque. And this is nice because when you make it smaller, this actually works better. It becomes easier and easier the smaller you make the device. And so, in fact, there's lots of work on so-called spin transfer torque magnetic random access memory, and the devices that are based on moving magnetic domain walls with spin polarized currents. The problem is, though, if you want to address one of the main issues of Moore's law, which is this increase in power dissipation, then using spin polarized charge currents is not very good, because the charge current obviously has dissipation with it, and the charge currents that you use in these devices are fairly large. So recently there has been lots of interest looking whether you can change magnetization states with electric fields. Whether by applying an electric field you can change magnetization or magnetic anisotropy, or there are so-called multi-ferroic materials which have a ferroelectric and ferromagnetic order, and by changing one you can possibly change the other. And then you can also take this idea to its full extreme and say, how about we just completely forget about charge currents or electric fields? Let's just see what we can do with pure spin currents, without any charge currents. And that's the focus of my research, and I'll tell you more about it today and tomorrow as we go along. Now, the reason why I also like this roadmap is if you look at this timeline. The year 2006 was the first year where there was actually a magnetic random access memory commercialized. In 2016, maybe we see the first devices based on spin polarized charge currents. So far there are some lab demonstrations